Why is state space crucial in reinforcement learning? Have you ever wondered how an artificial intelligence agent learns to make decisions in a complex environment? One of the key elements in this process is the state space. So, why is state space so important in reinforcement learning? Let's break it down. In reinforcement learning, the state space is the collection of all possible situations that an agent can encounter within its environment. Each state acts like a snapshot, giving the agent vital information about what is happening at that moment. This information helps the agent decide what action to take next. Without a well-defined state space, the agent would struggle to learn effectively. When we look at the basics, reinforcement learning involves an agent interacting with its environment. The agent observes its current state, takes an action, and receives feedback in the form of rewards. The ultimate goal for the agent is to learn a policy, which is a strategy that maps states to actions. This policy aims to maximize the total rewards over time. The state space is essential because it frames the problem, defining what the agent can observe and respond to. The size and nature of the state space can significantly impact the complexity of the learning process. If the state space is small and discrete, the agent can often use simpler methods like tabular Qlearning. This approach allows the agent to store and update value estimates for each state action pair in a table. However, many real-world applications involve larger or continuous state spaces, such as images from a camera or sensor data in robotics. In these scenarios, the agent must use function approximation techniques, like neural networks, to generalize across states instead of memorizing each one. Designing an effective state space representation is vital. Including too much irrelevant information can make the state space larger than necessary, which slows down learning and increases computational demands. On the other hand, omitting important details can hinder the agent's decision-making. For instance, a robot navigating a room needs accurate information about its position and obstacles but does not need to know the color of the walls. In some environments, the agent cannot fully observe the true state, leading to partial observability. In these cases, the agent works with observations that provide incomplete information about the state. This situation complicates the learning process and requires specialized methods, such as partially observable Markov decision processes. From an application standpoint, state space considerations are crucial in artificial intelligence tools like ChatGPT, DALL-E, and Midjourney. Here, the state might representing the current context or input data that the model processes. Efficiently managing and representing these states allows these models to generate coherent text or images based on user prompts. Similarly, productivity plugins that integrate artificial intelligence often depend on well-defined state representations to understand user context and provide relevant assistance. In summary, the state space in reinforcement learning defines the conditions of the environment that an agent perceives and reacts to. Its structure influences the choice of algorithms, the feasibility of learning, and the effectiveness of the agent's decisions. Properly defining and managing the state space is key to building reinforcement learning systems that perform well in complex, real-world scenarios.